All right, welcome to Lesson 2, Weight and Balance, Procedures for Weighing an Aircraft. What we're going to cover is we're going to go over how to prepare an aircraft for weight and balance, how to accurately calculate the center of gravity. We want to account for residual fuel, residual oil, and other fluids and determine whether we need to have the oil tanks and the water tanks full or empty. We'll identify the aircraft's specific weigh points. Where are we going to weigh it from? Are we going to use jacking points and put the aircraft on load cells on the top of the jacks, or are we going to actually tow it up on platform scales? And we're going to describe the aircraft's center of gravity range as listed in the type certificate data sheet. We'll review the graph that's in the type certificate data sheet, and we'll show you how you want to get that aircraft weight and balance, how it needs to fall inside that center of gravity chart that's actually in their graph that's actually in the type certificate data sheet. General concepts. Why reweigh an aircraft? Well, the obvious reason is to find the empty weight, and the second reason would be to find the empty weight center of gravity of the aircraft. Realize that over time, an aircraft is going to gain weight or possibly lose weight. We do a lot of modifications through the life of an aircraft, whether we're adding radio equipment or doing structural repairs or just dust and dirt in general, can change the overall weight of the aircraft. We want to make sure that that aircraft stays within the allowable weight limits. And we also need to realize that eventually when we're done working the airplane, there's going to be a pilot that's going to want to fly that aircraft, and he is going to use his calculations for center of gravity based on what we give him in the aircraft forms. So we could take an aircraft, we could lift the nose section here from the aircraft, we could take a rope or chain and hang it from the ceiling, a cable, and the aircraft, as it hangs down at an angle, and we can see it hanging down at an angle, notice you have your straight line coming through, and we would draw a line on that airplane straight up and down. Then we turn around and we take that same cable and we hang the aircraft from the tail, and again we look at that line coming straight down, and where those two lines intersect, right here, we have an X. The dead center of that X, that's the perfect center of balance for that aircraft. But in reality, could you see me doing that with a Boeing 787 hanging it from the tail in the nose? No, I don't see that happening. So scales are a more realistic option. We have a couple of different scales that we'll talk about and we'll actually use. We have a set of scales that actually sets on the ramp, and we just roll the aircraft up onto the scales. Another set of scales we'll talk about later are the load cells that we actually mount on top of a set of aircraft jacks. And we use those and we jack the aircraft, and then the load cells do the same thing as these scales are going to do. We're going to calculate the sum of the moment by determining the arm, where we're measuring the weight from, and the weight, what each scale is going to read. Remember, in order to calculate the arm, we need to know where the datum is, and then we take a measurement from the datum to the center of each wheel. So we'll take the sum of the weights, and we'll take the arm, and from there we can calculate the moment. And remember, we discussed earlier, the moment is actually the twisting force or the torque that's put on the aircraft around that center of balance. In this figure is going to represent it. If you take and look, the 0 on this figure here is going to be the datum of 0. And then as we go further back from the datum, we notice at 30 inches we have 50 pounds, and at 125 inches we have, at 60 inches we have 125 pounds, 95 we have 80 pounds, and then we have a center of gravity of 106.9, or a center of balance, if you will, and then we continue to add weight beyond that center of balance. But if we calculate the moment of this airplane to the left side and to the right side of that center of gravity, you're going to find that the moment numbers actually equal out, and that particular balance beam would actually balance at the 106.9 inches from 0. That's where it would actually balance. And it would stay balanced until we added weight or subtracted weight. Remember the seesaw? When we were growing up in the playgrounds, we had, as long as you had two people that were equal weights on the left side and on the right side of the seesaw, you were fine. That seesaw balanced perfect. But the minute that you had somebody that was heavier on one side and lighter on the other, all of a sudden that seesaw wouldn't balance. So in order to get it to balance, what did we do? We took that seesaw and we moved it a little bit to the left so that the lighter person had a longer datum, if you will, or had a longer distance, which created more torque. And the heavier person on the other side would have a shorter arm, if you will, and then when we did it all together, if you did the mathematics, you'd find out that the moment on the left and the moment on the right was the same, and that seesaw would balance. Okay, calculating center of gravity. To find the center of gravity, first we need to calculate the moment of each individual weight. So we'll take that 0 that we have here on the left-hand side, and that'll be our datum. Remember, that's where all our measurements are taken from. And we go with a 0 datum, and then we go out 30 inches, and we have 50 pounds. We go out 60 inches, we have 125 pounds. And we go out 95 inches, and we have 80 pounds. Center of gravity, or center of balance, if you will. And then at 125 inches, we have 50 pounds, and at 90 inches, we have at 145 inches, we have 90 pounds, and then at 170 inches, we have 100 pounds. So, in order to calculate the moment, again, we're going to do the weight of the object times the arm, or times the distance it is from the datum. Okay, to calculate moment for each weight, we need to know what the weight of the object is, and we know that, 50 pounds, and we need to know the arm, which is 30 inches. But how did we come up with that 1500? Well, real simple. So let's do a simple triangle right here, and let's go the moment equals arm times weight. So if I have a moment here, and I don't know what the moment is, so let's put my question mark here, equals an arm of 30 inches times a weight of 50 pounds, 1500. That's my moment, is 1500. I can do the exact same thing again. Get rid of this, make this disappear. Okay, and let's do the next one. So let's do our moment is going to equal, let's see, I have an arm of 60 times a weight of 125. What does my moment equal? Well, let's look. We have a moment of 7,500, or 7,500 inch-pounds of torque on that side of the fulcrum. That's pretty simple. Get rid of this. Okay. Hope that helps you to understand that a little bit. And we'll do more of those as we get further into the program. I'll give you some more problems to cover that. But let's back up here. Let's finish looking at what we have in front of us here. So we have 80 pounds at 95 inches, 7,600 inch-pounds of torque, or a moment of 7,600, and we do that all the way down. So 90 at 145 is 1,350, and then 100 at 170 pounds is 17,000. And we take all of those moments and we add them up, and we come up with a total of 52,900. And then we have a total weight of 495 pounds. Remember our little triangle that we just drew, that we had here. What did we say our moment was here? Our moment was 52,900, right? And then we come over here, what's my total weight? We're going to put our weight on this side over here, 495. So 52,900 divided by 495 is, better be about 109 or 106.9. So 106.9 times 495 is 52,900. Our center of gravity for that balance beam with those weights in those locations is at a point of 106.9 inches. And here we go. Remember this formula and remember this design. We will use this numerous times throughout the entire aircraft training modules that we're going to be doing. So, again, does it matter whether my moment or whether my datum was at 0, as you see in figure A, or at a negative 100 inches in figure B. It makes no difference one way or the other. If we do the math on both of them, we're going to find the center of balance is still going to be 106.9 inches to the right of the 0, or 106.9 inches to the right of the negative 100, which works out to be 6.9 inches. No matter how we do it, if the weights stay the same and the measurements are correct, we're going to get our center balance is always going to be in the exact same spot. Remember, manufacturers, when they make the airplane, they want to keep that datum forward of the aircraft as far forward as we can so that we're dealing with positive numbers. If you take Cessna Company with their 150 and their 172, their common datum point or 0 mark for datum is going to be the firewall. So anything forward of the firewall is a negative number, anything after the firewall is a positive number. But I have to admit, it's a lot easier when I'm working with just pure positive numbers. I'm not dealing with positives and negatives. Okay, so the critical point for the weight and balance of the aircraft, we have to calculate the aircraft empty weight, and then we have to calculate the aircraft center of gravity. If we don't get the accurate center of gravity on the empty weight, we don't give the pilot a reference point for when he loads the aircraft. So our job as a technician is to get the center of gravity, and then we can give the pilot that information so he can accurately calculate the loaded aircraft for safe flight. Okay. Theoretically, we could accurately get an aircraft center of gravity by suspending the aircraft from the tail and hanging it and drawing a vertical line from the top of the aircraft down, and then we could twist the airplane and hang it from the nose and draw another vertical line from top to bottom, and where those points intersect, that would be the center of gravity. Kind of like what we've got here on the right hand side. You could see the aircraft hanging from the tail. You can see how those lines intersect, and where they crisscross, that would be the center of gravity. But we know in real life we could never do that. So we're going to rely on jacks to go ahead and weigh the aircraft. We're going to go ahead and get the actual weight. We'll know where the jacks were placed, so we'll have the arm of the jack from the datum, and then when you take the arm times the weight, we can calculate the moment of that aircraft. In practice, the center of gravity is found by placing the aircraft on the scales, as we just said, and calculating the moment in the arm. Once you've calculated the center of gravity, just like we did on our seesaw, remember we had the seesaw that came across, and the moments on the left of the fulcrum and the moments on the right of the fulcrum, when they match, when they're even, that seesaw is going to balance. Doesn't make any difference how much weight is on the left or the right, so long as the moments, the weight times the arm gives us a moment. When that moment is equal, that seesaw is going to balance.